Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you.
Statically indeterminate beam. We have already discussed it in our previous lectures, that is statically indeterminate beams are those beams in which the number of reactions are greater than the number of equilibrium equations. So you can see that we have two-dimensional problem, and for two-dimensional we have three equation of equilibrium, that is sum of all the force along x direction is equal to 0, sum of all force along y direction 0, and movement is equal to 0. So statically indeterminate beams are those beams in which the number of reaction forces that is unknown and they are greater than the number of equilibrium conditions. So they are called statically indeterminate beam. Till our 9 chapter lectures in which we discuss part 1 and part 2, we only dealt with determinate beam. So in this lecture we are going to tackle with the statically indeterminate beam. Now you can see that this is a cantilever beam that is supported, fixed support at point A and a roller support at point B. So consider a beam with fixed support at A and roller support at point B. So from pre-body diagram we can find out that there are two reaction forces and a moment at point A, because this is a fixed support. So there is a horizontal reaction at point A as well as vertical reaction force at point A, and as well as there is a moment at point A, and at the end of roller support B there is only reaction force at point B. Clear? So from pre-body diagram, note that there are 4 unknown reaction forces. So here you can see there are 4 reaction forces. One is this, 2, 3 and 4. And this is two-dimensional problem, so we have only 3 equilibrium conditions. So the number of unknown reactions are greater than the number of equilibrium equations. So this is basically statically indeterminate beam. So we need a fourth equation or in order to solve this indeterminate beam. So as we know that we have a beam deflection equation that is represented as EYI is equal to integral of dx into integral of mx dx plus c1x plus c2. This is the same equation that we discussed in part 1 of this lecture. Clear? So we will use this equation along with these 3 equations in order to find the unknown reaction forces. But you can see if we use this beam deflection equation, so there are 2 other unknown constant, that is C1 and C2. So totally we have 6 unknowns. 4 is this one, reaction forces at A and B, and C1 and C2. So totally we have 6 unknown constants. Clear? So we will find them by using these 4 equations. So for this C1 and C2 we will apply the boundary conditions in order to find C1 and C2, and the rest equilibrium conditions are applied in order to find these reaction forces. So if you look at this beam, so the boundary condition at point A is mentioned over here. So you can see at x is equal to 0, slope is equal to 0 because this is a fixed support, and at x is equal to 0, deflection is also equal to 0. And at point B, at x is equal to L, because x start from 0 and it tends to r is equal to L. So for x is greater than or equal to 0 and less or equal to L. So at x is equal to L, the deflection will also equal to 0. So we will apply these boundary condition on this beam deflection equation in order to find C1 and C2, and then we will solve them by using equilibrium condition in order to find the unknown reaction forces. Clear? So by using this beam deflection equation, which introduces two unknown but provides three additional equation from boundary conditions. So you can see, if we use this equation along with another equation that is about slope, so that equation for slope is ei into theta is equal to integral of mx dx plus c1. This is the equation of slope. So we will apply the slope boundary condition on this equation, and we will apply x is equal to 0, y is equal to 0, x is equal to L, and y is equal to 0 on this equation. So we will have three equation, and 3 is this equilibrium equations. So total we have 6 equations, and we have total 6 unknowns as well. So we can easily solve this statically indeterminate beam. I hope it is clear to you now. Let's move further. In order to clarify it further, we will solve sample problem 9.3. After solving this problem, you will be able to fully understand the concept. Clear? So this is a sample problem 9.3. You can see for the uniform beam, determine the reaction at A. So you have to find the reaction at A, which is RA. Clear? And the second part is derive the equation for the elastic curve. So you have find the equation of deflection, that is y is a function of x, and then determine the slope at point A. So you have to find the slope at point A. Clear? So before solving this problem, first of all, you have to develop the differential equation of elastic curve. And how you will develop that? So for that you will need the moment equation. Clear? So you will find the moment equation, and then you will use this ei into d square y over dx square is equal to mx. So you will have this moment equation, you will put it over here, you will integrate it twice, and then you will have to apply the boundary condition in order to solve for reaction forces at A. And then when you have this deflection equation as well as slope equation, clear? So you can also evaluate the slope at point A. So let's move further. Clear? So if you section this beam at any point, that is from x is equal from 0 to at any length, let this length is x. Clear? So if I represent it over here, clear? So there is a reaction force, and this length is x, and there will be a shear force and the movement. Now if you look at this figure, the uniformly varying load is W naught, and it is for the total length L. Clear? So if you want to have if you want to section it at a distance of x, so now this let's wait for that. If you want to have this load for length x, so it will be W naught into x over L, because it is the W naught is for whole length, and this load is for x portion of total length L. Clear? So that is also represented over here. You can see that this is reaction force, this is the shear force and moment. Now this load is W, which is equal to W naught into x over L. So it is x portion of total length L. So W will be equal to W naught into x by L. Clear? Now this is uniformly varying load. So if in order to convert it into concentrated load, so this is, you can see this is a triangle, clear, right angle triangle. So this load is converted into concentrated load by using formula half of W, half of this load into length x. So you can see this is x, that is mentioned over here, and this is W, which is equal to W naught x over L and 1 over 2, because this is a triangle and the area of triangle is equal to half of W into X, which is W naught X over L into X. So this uniformly varying load is converted into concentrated load, and it will be acted at a distance of 1 by 3x from this side, because this is a denser side. Clear? And the remaining this portion from this point to this point, it will be 2 by 3x. Clear? I hope it is clear. Okay, so now we will apply the equilibrium condition, that is sum of the moment about point D is equal to 0. So you can see here they have taken the counterclockwise as negative. You can also take counterclock as positive, so both will give you the same value. Clear? Do not confuse yourself that here counterclockwise is taken as negative and clockwise is taken as positive. You can use your own convention, they will give you the same answer. So if you apply this moment equation, you can see this RA is producing a clockwise rotation, and that is multiply perpendicular distance is x, so RA into x. Now there is a concentrated load which is having magnitude half of omega W naught into x square over L, and perpendicular distance is 1 over 3 into x. So that is mentioned over here, plus this moment which is given over here. So when you solve it, so moment will be this one. There. Now you can see here the RA which is unknown, and we have to find this, but we have taken out the required equation that is about moment. So this is the moment equation. Now you will apply this equation, that is EI into D square y over dx square is equal to m. So instead of m, the m is equal to this value, which is RAX minus omega naught x cube over 6L. So this will be your equation with which you will play, and you will find all the other values and equation of deflections. So this is the equation. You can see when you integrate it once, so you will get the equation of slope EI into theta is equal to sum, and if you further integrate, so you will get EIY is equal to sum. That is solved in the next slide. So you can see that after integrating once, you will get this equation EI into dy by dx is equal to EI theta, that is for slope. Clear? And this is equal to this equation. If you further integrate it, so you will get this equation of deflection. Clear? Now you can see you have C1 and C2 which is unknown constant. Clear? So for that we will apply the boundary condition. So in our previous slides we have already discussed that at fixed support, clear, at fixed support you have slope is equal to 0 and deflection is equal to 0, and at roller support you have only deflection is equal to 0. So you will apply this boundary condition. So you can see we have two equations, but we can have three boundary conditions. So from here we can use we can have three different equations. So let's apply this boundary condition. Clear? So we will apply boundary condition. So at x is equal to 0 at this position, so deflection will be equal to 0. Let this equation is equation number 1 and this is equation number 2. So apply boundary condition at x is equal to 0, y is equal to 0. If you put in equation 2, because it is about deflection, so you will use this equation number 2. So if you put x is equal to 0, this term will be equal to 0, this term will be equal to 0, and this term will be equal to 0, and y is also equal to 0, so C2 will be equal to 0. Clear? Now if you put x, now we will move toward this side, so we will use this boundary condition. So at x is equal to L, theta is equal to 0, and equation for theta is this equation 1. So put in equation 1 this boundary condition you have to put in equation 1. So at x is equal to L, theta is equal to 0. So this theta will be equal to 0 and then this x will be replaced by L. So you will get this equation. Clear? Let this is equation number 3. Clear? Now the third boundary condition at x is equal to L, y is equal to 0. So you have to put again in equation to y because this is about deflection. Y is equal to 0. So at x is equal to L, y is equal to 0. When you put it in equation number 2, so you will get this equation. So this is equation number 4. Now you can see the equation 3 and 4 are two equations, and we can these are simultaneous equations, so you can solve it in order to find the reaction forces. Or simply you can see that if you take this C1 in terms of reaction forces and put it over here, so you will also get RA. So if you solve this for reaction forces, or if you solve this equation 3 and 4 simultaneously, so you will get the reaction force, which is RA is equal to 1 over 10 W naught into L. Once you get this reaction force, you can also put it in equation in equation 3 or in equation 4, so you can also get C1. Clear? So now you have C2 is equal to 0 and C1 is also calculated in term of you have RA, you can put it the value of RA over here, so you can also get C1. Once you have C1 and C2, so you can put them in equation number 1 and equation number 2. So you will get the slope equation and the deflection equation. Clear? So here we have replaced or substitute C1, C2 and RA in the elastic curve equation, that is this equation number 2. Clear? So when you put all the value of C1, C2 and RA, so the equation of elastic curves comes out to be this. And if you divide the both side of equation by E1, so this y is equal to this term, and this is the equation of elastic curve. And by using this equation we can find out the deflection. Now let me go back. In question it was given to find the reaction forces at A. We have find that, derived the equation of elastic curve. We have also derived that, determine the slope at A. Now we will find the slope. Clear? So you can see the reaction force has been calculated, then the equation of elastic curve has been derived. Clear? And now we will move toward the finding slope at point A. Now for slope we will use you can use this equation. When you put the value of RA and C1, you will get the slope equation. Clear? Or if it is difficult for you to substitute, so you can also use this equation of elastic curve. So when you take differential of this deflection with respect to x, so it will be equal to slope. Here they have taken out differentiate it once, so when you differentiate it with respect to x, so you will get the slope equation. So dy by dx is equal to this term. Clear? Now it is given that you have to find the slope at point A, and this point A is at x is equal to 0. So when you put x is equal to 0 over here, so you will get slope at point A, which is equal to theta A is equal to W naught L cube over 120 EI. So this was all about the topic of statically indeterminate beam. Clear? So I will also summarize it that whenever you have indeterminate beam, So definitely number of unknown reaction forces will be greater than the equilibrium condition. So you will apply the beam deflection equation, and then you will use boundary condition in order to find the unknown constant as well as the reaction forces. And further you can get the equation of elastic curve and slope, and you can also have deflection at any point, or at any point, and slope at any point as well. Thank you for watching the video.